So in today's lecture, we're going to talk about the Heisenberg uncertainty principle. So first, we're going to start with a heuristic motivation for the Heisenberg uncertainty principle. So what is the motivation? So let's take a particle. Suppose the particle has some wave function, which is given by something. So there could be a phase factor, but let's just ignore the phase factor for now. So suppose the particle is given by wave packet, which is a Gaussian. So if this is the wave function of the particle, we know that the momentum space wave function, which is given by A, would also be a Gaussian, because we know that the Fourier transform of the Gaussian is also a Gaussian. But importantly, if this Gaussian psi has a spread of delta, so that the Gaussian looks something like this, and this spread is delta, the momentum space Gaussian will have spread of 1 over delta. So the momentum space Gaussian will be like that. So that's the spread is 1 over delta. So if psi is very broad, A would be very tight. So this feature that the width of the wave function in position space is inverse of the width of the wave function in momentum space is a general feature. And of course, something we should mention is that when we are doing experiments, we are actually not dealing with wave functions directly, but dealing with probability density. So the probability density in the position space would be given by a Gaussian like this, and the probability density in the momentum space would be given by, so which is, and the forms of these Gaussians are saying exactly what we observed here. So this feature of wave function, that their spread, the spread of the probability and also of the wave function is inverse to each other, is something that is generic to all wave functions, not just the Gaussian. And for example, we can look at an extreme case. So suppose that we consider a plane wave at some specific time. So we have some plane wave, and it is a momentum eigenstate. It has a momentum p, and we are looking at it at some time t equals to 0. Then we know that the plane wave has the form, say, I px over h bar, and the conventional normalization is 2 pi h bar. Now this, of course, is not a normalizable state, because we can look at the probability density associated with this state, and that's just a constant. So this is not a normalizable state. But note that this state has a very definite momentum, which is p, and therefore if you look at the wave function in momentum space, it'll have the form of up to some normalization, it'll have a form delta of p minus p prime, which means that the momentum space wave function is peaked around the value of p prime equals to p. And so again, we see that the spread of the wave function in the position space and the spread of the wave function in momentum space are inverse of each other.